Hey guys, so in this video, I'm gonna kind of go over these, the next thing in your packet, which are these notes right here. I just want to show you what it looks like in your packet so that you know what I'm talking about. It's these kind of notes, which I know in your printouts and even on this, it's a little hard to see some of the text. Sorry about that. Printing in black and white sucks sometimes, but is what it is. But this is what I'm going to be going over, but in like an actual PowerPoint presentation. So in case you were wondering what part of the packet we are in, we are going to be working in, this kind of PowerPoint. Obviously, if you look at this, you can see that you don't have to do anything to it. You just have to follow along. And so I'm going to, take your words for it and assume that you're following along with me, even though you don't have to write anything. But this information will be on, this unit test in the future, whether we're in school at that point or because that might be past May 1st. I'm not really sure. It depends. Or, if we're still virtual, this information will be on that test. And a lot of this information is what you worked with in the foldable. So, you should find it as a review. Okay. And then the last part of this PowerPoint is going to be new stuff that we're learning. Well, I don't know if you learned it before I got there. And then we're going to be working on this part. Okay. So I will be doing that with you guys. And obviously this is something that you have to write on. So when I get to this part, I'll give you more instructions, but I'll have you guys do the same thing you did with the last notes where you'll send me a picture of this completed page. If you don't have a computer or if you don't have a printer to print it out on, that's okay. Just write it on a piece of notebook paper like you did for the review notes, okay? So I'll get started. Okay, so move my face down there. So this is, like I said, it's going to overlap with that foldable you just did, that History of Atomic Structure foldable. So we're going to talk kind of about those scientists today. It's a little boring, but we'll try to keep it interesting. So this, okay, we're working. Okay, so the first person we're going to talk about is Democritus, because we're going to go in chronological order, which means we're going to go in order of the earliest date to the latest date. So we're going to start with Democritus, and this was around 400 BC. So this is a long time ago, way back in Greece. And so he was a Greek philosopher. And so philosopher is someone who just thinks. They're not like a scientist per se. They just think, and they don't do any experiments or anything, but they just have ideas. So that's exactly what Democritus did, is he was the first person to kind of think about these ideas of atoms or small particles making things up existing, okay? So he thought about atoms' existence, and he thought that matter, which we know is, comes in three forms, is composed of tiny indivisible particles called atoms. And atoms, the Greek word for that is atomos. And atomos actually means cannot be broken down any further. So he thought that atoms were like the smallest thing you can get. We know now that that's not true, but obviously Democritus didn't do any experiments, so he wouldn't know that. But he was just thinking that all matter is made up of these tiny little things, but he had no experimental evidence. Remember, he was just a philosopher. So he didn't do anything to prove this. He was just like, this is what I think, you can believe it or not. Okay, so the next person we're going to talk about is, excuse me, John Dalton. And so he actually was a scientist, unlike Democritus, because remember, Democritus was just a philosopher. He didn't have any experiments. He just kind of sat and thought about things. But since John Dalton was a scientist, all of his theories and, things that he's stating are all supported by evidence that he found. He wasn't a chemist, though. He was a meteorologist, which is a little weird, but he still had these ideas and he still performed experiments. And so what Dalton did is he had these four major postulates. So these four major kind of points to his theory. It's a really ugly line, but I'm going to break those down for you. So his theory, his first postulate as part of his theory was that all elements are composed of indivisible particles called atoms. And so we know that an element is something like iron or helium or oxygen. And so he said, every kind of atom is composed of something that's indivisible, which means you can't break it down any further into particles called atoms. And so what he's saying is like atoms are the smallest particle, same kind of thing as Democritus, but obviously, like I said, he had experimental evidence. So he thought that these indivisible particles, so I'm going to put can't be broken down, because that's what he thought. He thought that atoms were the smallest particles, just like Democritus. The next one of his postulates is that atoms of the same element are identical. The atoms of any one element are different from those of another. And so what this means is, he's kind of true in terms of what we know today. So what he's saying is that, so say we have, an oxygen atom. All oxygen atoms are going to be the same, which is true for the most part. We might have a little bit of differences because, today we know we have electrons and neutrons and protons. So we know that atoms are divisible today, and we know that atoms of the same element can be different in the number of electrons they have and the number of neutrons they have. But for the most part, he's pretty correct. Because he's just saying that, if we have 10 oxygen atoms, they're all going to be the same. But those oxygen atoms are going to be different from something like helium. But those helium atoms are all going to be the same. Okay? So his next postulate is that atoms of different elements mix or combine in whole number ratios. And so basically what this postulate means is that, so you have, your atoms of different elements. So for example, you have your oxygen, and then you have, I don't know, carbon. Okay, we know oxygen and carbon come together to form carbon dioxide, carbon monoxide, stuff like that. So what he's saying is that atoms of different elements mix or combine in whole number ratios. He's saying that, like, you pretty much won't ever see something like half an oxygen atom bonding with a whole carbon atom or something like that. So you'll never have, half ratios. You'll never have half an atom, bonding to another atom. You won't have half atoms, you know what I mean? So the example is oxygen combines with hydrogen to form water in a 2-to-1 ratio, which we know is true because water looks like, we have the oxygen atom and then we have the 2 hydrogen atoms. So it would be 2 hydrogens, so 2 hydrogens for every 1 oxygen. And those are whole numbers, right? They're not decimals or anything. So the next postulate, and I moved my face up, so the next and final postulate is talking about chemical reactions, okay? And so we think of chemical reactions as, when we mix 2 things together and you get something new, right? That's the whole basis of a chemical change, okay? Because remember from your test and those worksheets that you did before I got there, physical changes are just changes to the shape of the molecules or changes to the state, stuff like that, where the actual substance doesn't change. So remember my example from the review video is me ripping up a piece of paper. It's still paper, right? But it's just ripped, so it changed shape. Or like that question from your test where it was like, is this a chemical or physical change? And it was melting ice down to eventually evaporate it as a gas, and that was a physical change because we're just changing shape. No, we're just changing states of matter. And so we could always reverse the process. We could always, condense that gas and, then freeze that liquid back down to an ice. So we're not changing what it is, it's still ice. And so he's talking about chemical reactions, which always involve a chemical change, right? So this is going to be where you have new stuff formed. You're actually breaking bonds and joining bonds and changing what the actual substance is. So he says chemical reactions occur when atoms separate, join, or rearrange, which is exactly what we talked about when we talked about chemical changes. So remember that little picture I drew where it was like my chemical change was like, I don't know, the circle connected to the square. And then we have like the triangle or whatever. That's a really bad triangle. And then the change is the breaking of one of these bonds to actually change what it is, to change the actual molecule. So this was like, oh, we still have the circle, but now the triangle is, has been broken off of that molecule. So now the molecule itself is different, right? Sorry, this is how I draw my arrows. I don't do that. That is an arrow. And so that's what he's saying. So this would be an example of him saying that chemical reactions occur when atoms separate, because we just separated the triangle from that molecule, and so we're changing it, right? He's saying you can also join them. Okay, so we can join them. Where are we? Okay, so say we have, let's go to yellow this time. I feel like you're not gonna be able to see yellow. Okay, so now let's say we have the circle and square bonded, and then we have the triangle separate, and then the reaction is the joining of these elements, well, the shapes in our case. So it becomes, square is bonded to triangle now, which is still bonded to circle. So, and that would be the joining, okay? And the rearranging would just be like moving. So do you see how the square is in the middle and the triangle and the circle on the outside? That would be like moving the square to the outside and moving like the circle to the middle or something like that. So that's what rearranging would be. So he's saying that's what a chemical reaction is. It's the separating, which I already drew, the joining, which is what I drew here, or the rearranging. And then he's saying that when you're doing a chemical reaction, the atoms themselves don't change. It's just, like the molecules that change. So the atoms themselves, so say you have oxygen and carbon again. When you join those together, it'll make, carbon monoxide gas, okay? But those atoms that are still in that carbon monoxide molecule are still carbon and oxygen. It doesn't change that. It's just now that they're bonded together. And so that's your reaction. And so he is correct in this postulate. Okay, let's continue. So next we have J.J. Thomson, which I'm going to hide this. You have J.J. Thomson. I'm going to move my face real quick. And what he did is he did the cathode ray tube experiment. And so I'm going to note something really, really quick. So when you spell J.J. Thomson's name, sometimes there's a P. And I'm going to go real quick to the next slide. Sometimes there's no P. Like there's no P right there. So either are right. I honestly don't know if you have put a P in J.J. Thomson's name or not. I don't know if it's Thompson or Thompson. I've seen both ways in textbooks, which is kind of strange, but it is what it is. So I just want to point that out. So if you see like Thompson versus Thomson, like you're not going crazy. Both are the same guy. Okay. So Thomson did the cathode ray tube experiment. And so what that is it's this little thing down here. And so he had an inert gas. An inert gas just means So inert just means like unreactive. Of course it won't. Right over there, whatever. But so an inert gas is an unreactive gas. And so in addition to that inert gas he had in this little tube thing here, he had two plates made of metal. And so one was positively charged and one was negatively charged. And so the reason he's using an inert gas, the reason he's using a unreactive gas is because he wants to make sure that the gas is not going to react with the positive and negative metal plates, okay? He just wants to see where the particles go to. He doesn't want them to react. He just wants to see where the particles, are attracted. And so what he found, and I'm going to move my head. What he found is that the particles in the gas were attracted to the positive plate. And what do we know about attraction between positive and negative? We know that opposites attract, right? So, oh my gosh. There we go. So we know the particles must have been negative because opposites attract. So the negative particles were attracted to the positive plate. And so that's what he found. And so then that leads us to our next slide. And it tells us that's how he discovered the electron, because we know electrons are negatively charged. And from this experiment, he found that the particles within the atoms of the inert gas were attracted to the positive plate, so they must be negative. So that's how he found these electrons. So J.J. Thomson is credited for discovering electrons from his cathode ray tube experiment. And so he believed that atoms were a solid positive sphere. And so that's what that looks like. So just like a circle with a bunch of little electrons just kind of thrown in there randomly on the sides of it. So he thought they were kind of on the outside. And so what they call this is they call it the plum pudding model, because like most scientists, he is a dead white guy from Europe. And so plum pudding is a European dessert that looks like this. It actually looks really disgusting to me, but that's what plum pudding looks like. So they termed it the plum pudding model because, English culture was very popular back then when this was discovered. And they're like, oh, this looks like that pie we make. So we're going to call it the plum pudding model, because if you look in this, all the little plums are scattered throughout this dough or whatever it is, just like how J.J. Thomson imagines the electrons are scattered on the outside of this atom. Okay, so that's why they call it the plum pudding model, because the electrons are scattered throughout kind of randomly, kind of evenly, just like the plum pudding. So next we have Ernest Rutherford. And so what Ernest Rutherford is famous for is his gold foil experiment. And so this is kind of what it looks like. I'm gonna hide this real quick. So what his setup kind of looked like is he had this coated screen, and then in the middle of this circular screen, he had this this piece of gold foil, which is why it's called the gold foil experiment. And then what he did is he shot high energy beams of alpha particles. And what alpha particles are, you're not going to need to know this, but just, fun fact. Alpha particles are just, they're just hydrogen nuclei. And so remember, the nucleus has, you should know this from if you ever studied atoms before. Nuclei have neutrons and protons in them. And so that's just what an alpha particle is. He's just shooting like hydrogen nuclei. Okay. So he's shooting these hydrogen nuclei, right? And remember, nuclei are just, I'm going to write this down so it helps you guys kind of understand this. I'll do this blue color or whatever. And I'm going to move my face yet again. I'm going to come your face. So what hydrogen nuclei are, like I said, nuclei are made up of protons, and remember protons are positive, and neutrons, which are, neutral. So I'm putting a 0 there because they don't have a charge. So he's shooting these alpha particles, which are these, hydrogen nuclei of protons and neutrons. So we know the alpha particles are going to be kind of positive because they have positive protons and neutral neutrons, which don't, contribute to the charge at all. So we're going to have an overall positive particle here, right? So he's shooting these positive alpha particles at the gold foil. Okay, and that's what this is showing you here. And he ends up discovering the nucleus. So how Rutherford found the actual nucleus, because I just said he found the nucleus from his gold foil experiment, is so I'm going to kind of zoom in on what's happening here really quick. Not really quick, I'm going to explain it. So this is kind of what it looks like up close, and let me draw for you the gold foil. So what I want you to imagine is that, okay, what's happening? So this is the gold foil, okay? So imagine that these are the atoms within the gold foil, okay? So the atoms of the gold foil have a nucleus, and it has this electron cloud, right? So I don't know if you guys are familiar from physical science, or, if you did atoms before I got there. I'm not really sure, but atoms are made up, well, we know this now, but atoms have a small nucleus, and then it's mostly made up of these electron clouds, which are mostly empty space. And so I'll kind of get to how Rutherford determined that. But so these are just the atoms of the gold foil. Okay, so he has the gold foil, the pure gold foil, and he has in gold foil, and gold is AU. Yeah, I think it's AU. And so he has all these AU atoms, okay, in this gold foil, because that's what makes up gold. And that's what he's shooting these alpha particles at, okay? So if the alpha particles are coming from this direction, going this way towards the gold foil, and remember, alpha particles are positive. So if he's shooting these positive alpha particles, and, when Rutherford is doing this experiment, he knows that alpha particles are positive. So he's seeing what happens if he shoots these positive particles at the atoms of the gold foil. Okay? And so what he sees is a lot of alpha particles just going through, because we see all this empty space here. And so alpha particles are just going to go through. He also sees a little bit of deflection. And so what this is remember that opposites attract, but same charges repel, okay? So if we have a positive alpha particle and we have a small nucleus, what do you think will happen if the alpha particle hits the small nucleus? Because we know nuclei are what charge? Nuclei are positive, right? We got it work. Come on. There we go. So nuclei are positive. So when we have a positive particle, because I already said it's positive, so we have a positive alpha particle getting really close to a positive nucleus, what do we think is going to happen? They're going to repel, right? So this is because we have repulsion. And so when we get really close to this positive nucleus, it's going to repulse the alpha particle. So the alpha particle is going to move away from the nucleus. And so that's why it's deflected, which is deflection just means it's, moved and the course is changed. What Ernest Rutherford also saw was that we have a rebounding. So when he's hitting the alpha particles, or when he's aiming the alpha particles at these atoms of gold, he is noticing that sometimes they rebound, okay? And so what's actually happening is the alpha particles are hitting the positive nucleus, and it's very dense, so it can't get through. And so since the alpha particle cannot get through this very dense, small nucleus, it's just going to hit it and bounce back, okay? So now we're going to look at his actual conclusions based on his observations, which is, the basis of science. So what he saw is, remember I told you that most of the alpha particles just went through. So most of the alpha particles just went through because, like, this path. So his next observation was that a few particles were deflected at small angles. So, like back here that I told you, because of this repulsive force between positive alpha particles and positive nuclei, that, when the alpha particles, since they're positive, when they get close to the positive nucleus, that repulsion deflects the path of the alpha particles. And because of that, he stated that alpha particles came close to something small and positive, because remember, positive and positive repel. And so that's how he determined that the nucleus of the gold atoms were positive. His last observation was that particles were very rarely deflected completely back. So remember, I showed you that sometimes the alpha particle, just hit straight on to a nucleus and bounced back and rebounded. That's what this last observation is saying, is that he saw that, but it didn't happen too many times, but when it did, it didn't pass through. And so that's how he knows that the nuclei are very, very small, and very densely packed, but also positive. So his conclusion that the particles were deflected at large angles, and that happened very rarely, is that, if something's very small, you're going to have a very small probability of actually hitting it because it's so small. But when, those particles did hit it and he observed that, he's like, oh, okay, well, it must be so dense in that little tiny area that the alpha particles cannot get through. So that was Ernest Rutherford's findings. So next we have Eugene Goldstein. So I'll move my head so you can read that date. And so Goldstein, this is the last particle to be discovered, was the proton, and he is the one that discovered that. And then we have James Chadwick, who discovered the neutron, okay, because we have that. So first we have the discovery of the electron by J.J. So these are discoveries of the subatomic particles. So first we have the electron by J.J. Thomson. And we have the nucleus itself as a whole by Ernest Rutherford. And from Eugene Goldstein, we have the discovery of the proton within the nucleus. And then Chadwick discovered the neutron within the nucleus. Okay? And so I already kind of talked about this, but I said that, as we went through each one of Dalton's postulates, so remember that was those 4 conditions I went through earlier. So as I went through them, I kind of told you, this is pretty true. This is, for the most part on the right path. Or I said, this is not accurate. So, with the discovery of atomos from the Greek philosopher Democritus, to him saying, atoms are indivisible and that's just what makes it matter, to Dalton's postulate saying, we have atoms and that's the smallest unit of matter, same kind of idea. We know that that's not true because after them came all these discoveries of, first we have the electron by Thomson, then we have the nucleus by Rutherford, then we have Goldstein with the proton, then we have Chadwick with the neutron within the nucleus. And so we know that the atoms can be broken down. So Dalton was wrong and Democritus was kind of wrong. To continue, we know that another one of Dalton's postulates was also wrong. So he said that atoms of the same element, so that would be having multiple atoms of an element like oxygen, are all the same, so are all exactly the same. And so we know today that that's not exactly true. And so, for example, we have something called isotopes. And isotopes are something we'll probably get into later, but isotopes, long story short, are atoms of the same element, but they have a different number of neutrons. And so that changes them a little bit, but we'll get into that later when we talk about isotopes. But atoms of the same element are not always exactly the same. And so an example of that would be, so if we have two atoms of oxygen, I keep using oxygen because it's easy. Oxygen's atomic number, I think, is 8. And so the atomic number, remember, tells us the number of protons is in that atom. And the only thing that has to remain the same in atoms of the same element is that the number of protons has to remain constant. So the number of protons will never change for atoms within the same element, okay? But the number of electrons can change. As long as the number of protons stays the same, it's still the same element. But say we have oxygen, which has 8 protons, and in a neutral atom has 8 electrons. The number of electrons can change, but as long as it still has 8 protons, it's still oxygen. Okay? So Dalton was also wrong in saying that all atoms of the same element are identical. That's wrong. So now we're going to talk a little bit about subatomic particles and just what they are, what charge they have, and what mass they have, because the mass will be helpful later on. So the first particle we have listed is proton. The symbol is just a P with a little plus. So if you ever see me writing really fast and you see a P with a plus, just know that means proton. The charge on a proton we already talked about, but it's positive. So it's +1, and then its relative mass is just 1. Okay? The next thing we have is neutron. The symbol for that is just N. And there's no plus or minus next to it because remember, neutrons have a 0 charge. It doesn't have a charge. It's just neutral. Neutral neutron. And then its relative mass is also 1. The final particle that we're going to talk about is electron, and that is going to be E minus. This is an abbreviation I use a ton. So if you ever see me write E minus, that means electron, and the charge for an electron is -1, and then its relative mass is 1 divided by 1,840, or for our purposes, we're going to say that its relative mass is 0. It weighs basically nothing for our purposes. So when we get into talking about the masses of atoms, we're usually going to add the number of protons plus the number of neutrons, but we're not going to add the number of electrons because electrons weigh nothing. Okay? So those are our 3 subatomic particles. Those are their charges, those are their masses, and that's the symbol I might use to write them. The location of the particles, so protons, I said this already, are in the nucleus. Neutrons are in the nucleus, and then electrons are in the electron cloud outside the nucleus in energy levels. And we'll get to that later on in this chapter. And I have a ton of practice about that, so you'll definitely feel hopefully comfortable about it. But just know protons, neutrons, nucleus, and electrons are outside of the nucleus in the little cloud. Last thing, in a neutral atom, so this is very important. So I'm going to move my head again. So in a in a neutral atom, neutral is when neutral is when you have a charge of 0. So your charge is 0. And so when an atom is neutral or 0, that means the number of positive protons has to equal the number of negative electrons, okay? So when that happens, so for example, in oxygen, because it's my favorite example apparently, you have 8 protons, and if you have a neutral atom, you need 8 positive electrons to make that neutral, okay? So the last part of this video, and I know it's long, I'm very sorry, but this last part of the video is what you are actually going to be writing down, because my PowerPoint is green, the student version is white. So this is what it looks like in your packet. It follows the slides we just finished going over. So in your packet, it's right here, and this is what you're going to send me a picture of, okay? And this is the slides I'm going to go through. So I'm going to zoom in on this. So maybe I'm not. Anyways, so this is the part where we're going to talk about subatomic particles in detail. So the first thing you need to know about subatomic particles, the word subatomic, I say very fast, but I do want you to know what exactly it means. So sub means smaller than or within, and atomic obviously means atom. So if you put it together, it means smaller than atom. So you ask, what's smaller than an atom? So the parts within the atom that we just finished talking about. So we found out the discoveries of the electrons, of the nucleus, which contains the protons and the neutrons. So those are the 3 subatomic particles that there are, and we're going to kind of talk about those in detail. And if you need to finish writing, you can pause this part of the video so you can finish writing, because I'm not going to pause myself so you can write, but if you need to pause the YouTube video. So we have several different kinds of particles. This is not in your student version because I think it's a little bit confusing, but this is just telling you we have matter and we have particles within the matter, and those particles are molecules and atoms, and in those atoms we have nuclei, and then we have forces that keep everything together. So this is a very fancy table just saying that we have matter. Matter is made up by atoms. Atoms contain nuclei and electrons, and within those parts of the atom, what holds them together are these forces. You don't need to know those forces or anything, so don't get overwhelmed. So the first thing we're going to do is we're going to draw an atom. Okay, so we're going to go ahead, and I know you have to do this in your packet too. See, this is where you have to draw the atom. Just draw everything that I go through on here. So first we have, come here. So first I'm going to do the nucleus, okay? And so I'm going to make this the nucleus. Come on. This is going to be the nucleus. The nucleus goes in the middle for our purposes, okay? So the nucleus is going to go in the middle, so you can already draw a little circle inside the bigger circle. And what do we know that we just kind of talked about that's inside the nucleus? What particles are in it? So we have protons inside the nucleus. So I'm just going to throw these little protons in here. And then we also have neutrons. Put these guys in here. So what you need to take away from, no, don't move that. What you need to take away from this is that all the protons and neutrons are inside of the nucleus. So continuing, the last thing we have to put onto the diagram here are the little electrons, and the electrons go on the outside circle. So I'm going to move them out here. That's going to go there. So do you see how I try to place them kind of on the outside circle? They sit on the circle, okay? Not in it, not outside of it, but I tried to put them on the circle. But of course, like, the computer isn't my best friend right now. So that is how you draw the atom. And so this kind of goes through it, but I just did it interactively with you. But the nucleus is in the middle, then you do the protons, then you do the neutrons, and then the electrons on the outside. And so what holds the atoms together is called electrostatic force. And so it's between the protons and electrons. And so the protons and electrons are opposite charges, right? And so we don't really know why the electrons don't just like float away, but we think it's because of this electrostatic force. Because protons, since they're positive, attract the negative electrons, so they won't go very far, okay? They're going to stay in their little electron cloud out here. And so we note that the charges are equal in size, even though that they're equal in charge. The charges are equal, even though the actual size of the particles is not. So we see that the size of the electron is significantly smaller than the size of the proton. It matters with the weight, because remember, the weight of the electrons is very small, but the weight of the protons is 1. Same with the neutrons is also 1. But the size of the particle doesn't have anything to do with the charge on it. This is -1, and the protons are +1. Okay? And so you need to know that this electrostatic force pushes, the electrons so they're as far away from each other as they possibly can be, but it keeps the electrons close to the nucleus as they can. And then the last thing we're going to talk about is the nuclear force. So the nuclear force is going to be between the protons and the neutrons, and then it acts over a short distance. So the nuclear force only applies to the nucleus. It does not apply to keeping the electrons in, because it only acts in a short distance. It only acts within the nucleus. It doesn't act over, the distance from the nucleus to the electrons. That's what the electrostatic force is. The nuclear force is just acting within the nucleus, and then it's just what is between the protons and neutrons. Okay? So that's the part I wanted you to send me a picture of. My laptop is about to die, if you can't see down here, so I'm going to go charge it. If you have any questions about this, let me know. I'll give you several days to finish this video. I mean, obviously, if you got to this point, you're finished, so it doesn't really matter at this point. But if you have any questions, let me know, and we will do practice over it next. That's the next thing we're going to do, is practice over this concept. Okay? All right. Thank you.